Hey everybody, how you doing? Welcome to Coconut Spaceport. Today I am talking about a mathematical geometric figure that I figured out some time ago. It actually took me about 4 or 5 years, and I have finally put it up on the Coconut Spaceport gift shop, available for your enjoyment on all kinds of products. So today I just wanted to talk about the figure itself and how I got there, sort of. When you've had enough of Earth's dumb stuff, come to Coconut Spaceport. So today I just want to talk about the figure itself. Okay, let's have a look at it. Looks pretty simple, right? I mean, it's just a few grids and a circle and then a horizontal line sticking out all the way to the right. And that is our circumference. Now, what's weird about this? Well, you should not be able to find circumference in geometry, and technically you can't. So let's just pause right there. I don't want geometers and mathematicians coming for me about this, because this is only an approximate, okay? Now understand that the world kind of runs on approximates. Now I know that's not the case in mathematics. In mathematics, we want everything to be perfect and neat and precise, but the problem is that when you have what are we calling this? When you have the circumference of a circle, what we're actually dealing with is pi. And pi is an irrational number and is a transcendental number. And you can't properly portray that in geometry in a straight line. But let me make a quick correction, because it is true that sometimes you can have an irrational number like the square root of 2 that can be perfectly portrayed in geometry, but something like e or pi, which are transcendental, nope, nada, never. So we're not going to worry about that, because what we're talking about is an approximate. Because we know that geometry has a fundamental limit that you can never properly show an exact transcendental number represented as a horizontal line. Well, we understand that, we accept that as our baseline, we throw it out. And I'm not saying we ignore the fact, all I'm saying is we accept that geometry is an imperfect system for these types of numbers. And so the best we can do in geometry is an approximate. And knowing that, now we can have a little bit of fun, right? Now we can say, okay, we get that it's never going to be perfect, it's never going to be exact. Fine. So now we can look at what's the closest we can get. You know, all through history, people were obsessed with circles, with pi, with squaring the circle, which we can get into in a little bit if we want to, but it's basically about converting the area of a square into a circle, or a circle into a square. Here's a quick example. On the left, we have a circle with a standard radius, and when you look down below, that radius translates into an area of pi. So we know that the circle has an area of pi. Here's the problem. In order to have the square on the right, which is a quote-unquote same area as the circle, in order for that to be true, then each side of the square, because you multiply them together, has to be the square root of pi. So then what we're saying is one side of the square is equal to a perfect length of the square root of pi, but we already know, we've talked about this, that you cannot have a straight line length of pi or any derivative of pi. It just doesn't work. So that's why for these exercises and for my figure, we are only talking about an estimate, the best estimate of a straight line length of pi. So what I found, and this took a long time, was a really, really good, simple approximate of pi, of a circumference within geometry. Now, how is this different than other attempts in the past? Well, there are many versions of coming up with pi in geometry, approximate pi in geometry. But even Ramanujan came up with this very, this very complicated, sophisticated but complicated version of approximating pi within geometry. And look at this thing. Do you see how complicated that is? Do you see how this is about 27 different steps just to get to a number? Now, the number that he got to is really good. And here's the interesting thing about that. This is based on a known ratio, which gives you a really good estimate of pi. And I don't know the history of this, but I think he actually started with that estimate and then worked backwards. So he knew this ratio and then said, how can I construct geometry that represents this ratio? So this is another example of why you can't do pi exactly in geometry, but you can represent pi approximately because the ratio acts as the approximate. So Ramanujan did this. He took this ratio and then converted it, if you will, into geometry, and then you get this. So let's look at Ramanujan's approximation, which is amazing, it's excellent. But now let's look at mine again. Ramanujan, mine. Do you notice the difference? One looks like you need a master's degree to understand it. The other one, a third grader could understand. It's literally just two grids, 5 by 5, identical, one tilted at 45 degrees, that's it. 45 degrees is the simplest angle other than a right angle. So it's just tilted at a 45 degree angle, the corners touch, and then you have, within the 5 by 5 grid, you have a 4 by 4 circle. And then you draw a line straight through the circle and out. Maybe I should be doing it the other way. Draw a line straight through the circle and out. And then we literally only have one more step in order to get a really good approximate circumference of that circle. And all you do is you draw a line from the circle down to the outside corner and then back up to the line in a right angle, and that's it. This figure that I created actually shows you what the circumference looks like. If you were to roll that circle out and stop it, that's how big it would be. Which brings us to the question, how accurate is my figure? So you can make up lots of figures that are really crappily accurate, meaning not very accurate. And of course, Ramanujan's is amazing because it's based on a detailed proportion that gives you a really highly accurate estimate of pi, right? So that's cool. That's a really cool thing that he did. But nobody wants to make this figure with 27 steps. I mean, a nerd, a geek, someone in high school, college, they might be interested in it. It's a lot of steps. So mine literally lets anybody take two squares. They could be tiles. You could have two tiles, you tilt one tile, and now you have your figure, you draw your line, boom, boom, there's your circumference. That's why this is kind of amazing. Okay, so how accurate is it, right? So if we oh boy, let's see, how do we say this? If we can pretend this is a true circumference or true pi, and let's expand it so far that this true pi or this true circumference is the length of 10 football fields, explode it out to that length. So then we say, okay, let's take my crappy little figure and see what my figure says the correct answer is. Well, my figure is off by only 1 inch. That's about this much. It's the tip of your finger. 10 football fields out. My figure is only off by the tip of your finger. It's not bad. It really is not. So what's cool about this? Well, in any kind of approximate geometry, there's two things at play. One is the accuracy and one is the simplicity. So the thing that my figure contains that I think a lot of other approximate geometries for either pi or squaring the circle or circumference contains is its absolute effing simplicity. Okay, so look how simple again. Let's look at the figure again. Look how simple this is. So it has an unmatched simplicity that still gives you a pretty good accuracy. It's out to about 5 decimal places. Gives you a pretty good accuracy, so much so that in 10 football fields length, it's only off by 1 inch. Okay, one more thing I wanted to show you. We already compared my figure to 10 football fields of length, right? But Just to give you another perspective, I also mocked this up showing you how big the Great Pyramid at Giza would be compared to this 10 football field length. So it would literally be 4 Great Pyramids and then another 3/4 of a Great Pyramid. That's how huge we can make my figure and still have it only be off by 1 inch. Right? So that's pretty amazing. So you take those two factors together and that tells you whether there's a wow factor to your geometric figure or not. Ramanujan's is amazing in accuracy, right? So his accuracy is up here, but you almost lose points for complexity. If you have to do 100 steps to get this accuracy, it gives you kind of like a medium score. So I'm not saying mine's better because mine is way less accurate. But what I am saying is, as a combined score of pretty okay accuracy and simplicity that is through the roof, it brings the score to around here. It's a pretty amazing figure. Hey guys, I just had to jump in here a minute, cut off the other version of myself. I realized that this video was going long and that my explanation at the back end is just taking too much time up, and it was gonna make it this ultra long video that no one's gonna watch. So I'm gonna break this up here and continue with a second video with my full explanation of how I arrived at this figure. But for now, I'm just gonna wrap this video up and just say, yeah, I'm very proud of this figure. I know it's just an approximate and that's kind of looked down upon a little bit in the mathematical community, but that's okay. I still think there's some real value to it. And again, I will explain to you in the next video about how I arrived at this figure, just to show you that I didn't just pull this out of thin air and that it actually took a lot of thought. So that's it. Thanks for watching this video. I will see you guys very soon in the next one.